We've been working with implicit differentiation, and we've seen that implicit differentiation was helpful when we're finding derivatives of inverses. We're going to start with, say, like the sine. The sine is a function that begins with an angle and ends up giving you some ratio, like the opposite over the hypotenuse. Then the arc sine, or the inverse sine, does the opposite thing. So if you have the ratio, it tries to give you back the original angle. The problem with that would be if you look at the graph of sine. So here's the graph of the sine of x. If you give me an angle, let's say you give me pi 6, so you give me that angle pi 6, then out comes 1/2. There's a single answer there. But if you try to go the other way, if you just have the ratio, let's say you told me that the ratio, the output of the sine was 1/2, and asked me what's the original angle, you want me to go backwards, then one possibility is pi 6, but then you can see that another possibility here is 5 pi 6. In fact, there are infinitely many possibilities. So we can keep going over in both directions. Since sine is this periodic function, it's got trouble. We'd say it fails the horizontal line test. Its inverse isn't a function because you can draw a horizontal line that crosses the graph in more than one place. So in order to solve that issue, what we do is we cut off our function, the sine, so that it will pass the horizontal line test. And with those restrictions, now we assume that if you give me a fraction, then I can only give you an angle between minus pi halves and pi halves. So we could have cut it off in different regions. We would have gotten what were called different branches of the inverse sine function. And this is principally what's done, usually what's done, and so we call it the principal branch of the arc sine. You can just assume that that's true. Now, all of these trigonometric functions have to be cut off in order to have inverses, and they basically either we principally cut them off between minus pi halves and pi halves. That's what we do for arc sine, arc tan, and arc cosecant. The other ones, like arc cosine, arc cotangent, arc secant, we cut off between 0 and pi. So in each case, we know that these inverse functions are going backwards. They're starting with some ratio and giving back an angle, but the angle is going to be in some specific range, either between minus pi halves and pi halves, or between 0 and pi, depending on the function. That's all the background that we need in order to start finding the derivatives of these. So let's say that we want to find the derivative of the arc sine of x. So we want to see what's that derivative. So basically, let's say that y is the arc sine of x, and we want to find dy dx. Before we do that, I just want to point out something. The cosine of the arc sine of some ratio x is going to be the square root of 1 minus x squared. There are a couple ways to see why. One way is just the usual Pythagorean identity. You know that if you take the cosine squared of an angle plus the sine squared of an angle, then you're going to get 1. I can solve this for the cosine. The cosine squared of an angle is going to be 1 minus the sine squared of the angle. So the cosine of the angle will be plus or minus the square root of 1 minus the sine squared of the angle. Now you choose the plus or minus based on the quadrant that the angle lies in. If the angle alpha is over here in either the first or the fourth quadrant, then the cosine should be positive because the cosine is the horizontal distance and you're moving out. On the other hand, if the angle's over here, either in the second or third quadrant, then the cosine should be negative. Now, we're talking about taking the cosine of the arc sine. So remember, the arc sine had a restriction on it. It gives you an angle, but that angle has to be between minus pi halves and pi halves. In other words, it has to be over here, either in quadrant 1 or quadrant 4, which means that the cosine of an angle over there is going to be positive. So that should be the square root of 1 minus the sine squared of the arc sine of x. So in this particular case, if we're talking about taking the cosine of an arc sine, we know our angle is in a place where the cosine will turn out to be positive. Now, if you look at this, we're taking the sine of the arc sine and then multiplying it together. But by definition, the arc sine of x is an angle whose sine is x. So this is going to turn out to be 1 minus the sine of the arc sine is x, and we've got sine squared, so it's going to be 1 minus x squared. Now we can go ahead and proceed to take the derivative once you accept that that's true. So we have y is equal to the arc sine of x which means y is the angle whose sine is x, the angle between minus pi halves and pi halves, whose sine is x, so the sine of y is x. Now we can use implicit differentiation. If we take the derivative of both sides with respect to x, this is a chain because y is a function of x inside the sine, so we get the derivative of the outside, which is cosine, evaluated at the inside, times the derivative of the inside. The derivative of x with respect to x would be 1, and therefore dy dx is 1 over the cosine of y. Now, we know that y is the arcsine of x, so let me substitute that in right here, and we have 1 over the cosine of the arcsine of x. And we just got done pointing out that the cosine of the arcsine of x is the square root of 1 minus x squared. So now we know what the derivative of the arcsine is. The derivative of the arcsine is 1 over the square root of 1 minus x squared. Notice if you look at this function, it would only make sense if x squared was smaller than 1. In other words, if x was a number between -1 and 1, then this wouldn't be so big that it would overwhelm the 1 and give us a negative answer, which is perfect because the sign always gives a value between -1 and 1, and so it stands to reason that the arcsine could only handle values between -1 and 1, and its derivative has a similar issue. Let's do it for cosine inverse. Again, you could show that the sine of the cosine inverse is the square root of 1 minus x squared. It's almost the same thing. You could trace through it if you like, but you're going to use the Pythagorean theorem. Since the cosine inverse is an angle between 0 and pi, that's a place where the sine is always positive. So technically there could be a plus or minus here, but for this particular angle, the cosine inverse of x, it's got to be plus, because that's an angle between 0 and pi, and if the angle's between 0 and pi, it's in the first or second quadrant, and if it's in the first or second quadrant, the sign is positive. So let's do what we did again. We're going to say, all right, if y is the cosine inverse, then the cosine of y is x, right? Because cosine inverse gives you the angle whose cosine is x, that's between 0 and pi. We're going to take the derivative of both sides. We get the derivative of the outside evaluated at the inside times the derivative of the inside. And the derivative of x with respect to x is 1, so dy dx is -1 over the sine of y. And we're talking about taking the sine of y, but y is the cosine inverse of x, so I just replace that. And now we can just apply this identity that we just noted. Dy dx is -1 over the square root of 1 minus x squared. The derivative of the arc cosine is almost exactly the same as the derivative of the arc sine. It just has a negative inserted in there. Okay, 2 down, 4 to go. Let's do it for the arctan. Now before we do that, I want to point out that the secant squared of the arctangent of x is 1 plus x squared. That's because of our Pythagorean identity. The secant squared of an angle is 1 plus the tangent squared of that angle. So if you give it the arctan, then you're going to have the secant squared of the arctan is going to be the same thing as 1 plus the tangent squared of the arctan. Okay, let's see. Tangent squared means tangent times itself. Of course, the tangent of the arctan is the angle whose tangent is x, so that should be 1 plus x all squared because it was tangent squared. With that, it's easy to find the derivative of the arctan. Again, we start out the same way. If y is the arctangent of x, then y is the angle whose tangent is x. So arctan is starting with some ratio and giving you an angle. It gives you the angle whose tangent is x. So we take the derivative of both sides. The derivative, this requires the chain rule. The derivative of the tangent is the secant squared. So the derivative of the outside evaluated at the inside times the derivative of the inside. And the derivative of x with respect to x is 1. So dy dx is 1 over the secant squared of y. But y is the arctangent. And we just showed by that Pythagorean identity, secant squared is 1 plus tangent squared, that the secant squared of the arctangent of x is 1 plus x squared. So now we know the derivative of the arctan. Works almost exactly the same way for the cotangent. The cosecant squared of the cotangent inverse is 1 plus x squared. It comes again from that identity that 1 plus the cotangent squared of alpha is equal to the cosecant squared of alpha. You can show using this identity that this is going to have to be true. Okay, so knowing that, then, if y is the arc cotangent of x, we know that y is the angle whose cotangent is x. We take the derivative of both sides with respect to x. Now the derivative of the cotangent is the negative cosecant squared. Oh, and we get dy dx because of the chain rule. And then that's equal to the derivative of x with respect to x, which is 1. So solving for dy dx, we get negative 1 over the cosecant squared of y. But y is the cotangent inverse, so we have the cosecant squared of the cotangent inverse of x. And we know from this little note that we could show that cosecant squared of cotangent inverse squared is 1 over 1 plus x squared. So this, the derivative of the cotangent inverse isn't that interesting. It's just the opposite of the derivative of the tangent inverse. Okay. Now, our last two are a little bit trickier. There's an identity that we need, that the secant of the secant inverse of x times the tangent of the secant inverse of x turns out to be the absolute value of x times the square root of x squared minus 1. You get this absolute value because there's some fancy footwork going on here. See, the secant inverse always gives you an angle between 0 and pi, but then if you take the tangent of an angle between 0 and pi, sometimes it's positive, sometimes it's negative, and it depends on what the ratio is. So the original ratio x here is, and so that's why the absolute value comes up. So that one's a little bit tricky. Let's just assume that we don't want to see it done. It'll make your eyes glaze over anyway. But after that, it's easy to do this. Again, if y is the arc secant of x, then y is the angle whose secant is x. The derivative of the secant is the secant tangent, so we get the derivative of the outside evaluated the inside is the secant of y times the tangent of y, and then from the chain rule we have to multiply by dy dx. Over here we have 1, so dy dx is 1 over the secant of y times the tangent of y. And of course, y is the secant inverse, so we get the secant of the secant inverse of x times the tangent of the secant inverse of x. And we said with a little bit of work we could show that that's equal to the absolute value of x times the square root of x squared minus 1. The cosecant inverse works pretty much the same. You've got the same basic identity. Again, there's that's clearly cosecant inverse of x is x, but we get this absolute value because of a consideration here. Cosecant inverse, since it's related to the sine, gives you an angle between minus pi halves and pi halves, and in that range the cotangent is sometimes positive and sometimes negative, and so we have to consider some cases, and it turns out this is the right thing. So with that identity, it's easy to show that if you take the derivative, let's see, the derivative of the cosecant is the negative cosecant cotangent, so the derivative of the outside evaluated the inside times the derivative of the inside, and that's equal to the derivative of x with respect to x, which is 1. So dy dx is 1 over the negative cosecant of y cotangent of y, and that's negative 1 over, because of this identity and because y is cosecant inverse of x, that's 1 over the absolute value of the square root, absolute value of x times the square root of x squared minus 1. So to sum up, we have the derivative of the arc sine is 1 over the square root of 1 minus x squared. The derivative of the arc cosine is almost the same, it just has a negative sign. The derivative of the arc tan is 1 over 1 plus x squared, and the derivative of the arc cotan is almost the same, it just has a negative sign. The derivative of the arc secant is 1 over the absolute value of x times the square root of x squared minus 1, and the derivative of the arc cosecant is almost the same, it just has a negative sign. So basically you have 3 to memorize: sine, tangent, and secant. Once you have those, you can throw negatives in front of them to get them for the corresponding cosecant, cotangent, and cosecant inverse.